learning about energy. Kinetic energy, as you may be familiar, is the energy of objects that are in motion. So anything that's moving has kinetic energy. My arm, when I wave at you, is moving. It has kinetic energy. A ball rolling across the floor, a vehicle moving very, very quickly, all of them have kinetic energy. To derive an equation for kinetic energy, we're actually going to work backwards and go back and talk about that concept of work again. And through that, we will get to kinetic energy, because the two are related. So remember that our formula for work is equal to force times displacement. And since force can also be written as mass times acceleration, according to Newton's second law, we can also write work as work is equal to mass times acceleration times displacement. Yep. So we would write that as W equals ma delta x. And now we can take this lovely equation and connect a previous concept back from when we learned kinematics, which is our equation velocity final squared equals velocity initial squared. I believe that should be a plus sign and not an equal sign. That's a typo on my behalf. Plus 2 times acceleration times change in displacement. If we manipulate this equation around, move things around to get the acceleration, and the displacement on one side of the equation together, then we would get acceleration times displacement is equal to mass times velocity final squared minus velocity initial squared divided by, and all of that divided by 2. If you then substitute this equation into the equation for work, what you wind up with is an equation relating work and kinetic energy. So work net, so the total work for a object, is 1/2 mass times velocity final squared minus 1/2 mass times velocity initial squared. And this, I'll give you a chance to write that down. This 1/2 mass times velocity squared in physics is what we know as kinetic energy.
It doesn't matter if it's initial or final, it's just the velocity.
Because kinetic energy is a scalar quantity, so we're actually using speed and not velocity. So kinetic energy is equal to 1/2 mass times speed squared. In this equation, they've separated out, in the equation we were just looking at, they talked about initial and final speed, and that's fine, and that's because of that equation, but just kinetic energy is just half of the mass times the speed squared. So in that case, what they were actually showing you was final kinetic energy minus initial kinetic energy. We'll come back to that concept because we're going to talk about how work and kinetic energy are related. Kinetic energy is a scalar quantity, meaning it does not include a direction. Yay, right? No adding vectors. The unit for kinetic energy and for every other type of energy that we're going to discuss the rest of the chapter is the joule, which, if you will remember, is also the unit for work. So they are one and the same. Same unit. As you can see, kinetic energy of an object depends both on that object's mass and on that object's speed. So if you have two objects that are traveling at the same speed, but one is more massive than the other, the one with more mass will have more kinetic energy, which you can understand as a concept if you've ever stood in the path of, a tennis ball versus a baseball, right? One of those has more mass, and as a result has more energy, and as a result you feel the impact from it a lot more significantly. Let's look at an example problem. Okay? Silvana Cruciata from Italy ran 18.094 kilometers in 1 hour. It's a lot of kilometers. Consider that 5 kilometers is approximately 3.01 miles. So it's a lot of miles that she ran in just 1 hour, which at the time was a world record. Okay, so if her energy, her kinetic energy, was 694 joules, what was her mass? So grab that equation that we had and see if you can't calculate her mass. Okay, so to begin with, what we're going to do is use our equation for average velocity to find her speed. Because, of course, velocity is just speed with a direction, so we can use this equation to get it. So our velocity average is going to equal our change in displacement divided by our change in time. So we can take our displacement, 18.094 kilometers, and divide it by 1.000 hours, which would come up with, same number as our speed, but this time it'll be in kilometers per hour. So it just has a new unit on it. And then we can take that and plug it into our other equation, which we have, which is our kinetic energy is equal to 1/2 mass times velocity squared, or speed squared. Okay, so if we have two things we can do. We can either plug in all the information that we know and calculate it out, or we can isolate, we can manipulate it to get mass by itself. Either path is fine. So we could just say, we have 694 joules equals 1/2 mass times our 18 number squared, and then do the math and solve for it. Or we can manipulate the equation to get mass by itself, in which case we would have mass equaling 2 times the kinetic energy divided by the velocity average squared. In either situation, you should wind up with a mass of about 55.0 kilograms.
Yep, I forgot square.
How do we feel in terms of using this equation?
Except for the fact that I just fixed it. I'm still getting
Let's back up and just see if we can do this. Let me wipe my screen. So we have 694 joules is equal to 1/2 mass times 18.094 kilometers per hour squared. So we're gonna do this number, and then we're gonna divide both sides by whatever that is, right?
roughly around 320.
And then in order to get rid of the 1/2, we're gonna multiply this by 2. So when you do that, you still don't come up with the same answer that I'm coming up with?
Because when I divide the 694 by
Our problem is that joules is Newton meters, and we have a speed that's in kilometers per hour. We need a speed that's in meters per second in order to come out with the correct answer. So we needed to convert. That's the issue here.
so which one would you end up converting?
You convert meters per hour, or kilometers per hour into meters per second, and then you would get the correct answer.
Gotcha.
Or you should anyway.
says joule.
This is why dimensional analysis is really important. Because otherwise we it's very easy to forget that we want our answer to be in kilograms, but the units we have are newtons and meters and joules and all of that jazz. So we have to break them down into their components. So joules is newton meters, and newtons are kilograms times meters per second squared. So we have to have units in meters per second if we're going to multiply by anything that's in joules.
Otherwise, it does not work.
Does not compute. No, 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 no. They were tricky. They tried to trick us. This is also why at the senior of high school year and up, it doesn't matter if your book has all of the answers in the back if you cannot do the work to get to them.
For sure.
Okay. Okay. Example problem done. Whew, we made it through. So you can see from the equation that we derived earlier, the work net equals 1/2 mass times the velocity final squared minus 1/2 mass times velocity initial squared, that if you take final kinetic energy and you subtract initial kinetic energy, you get work as your result. So this is what we call the work kinetic energy theorem, which means that work is equal to the change in kinetic energy for an object. To use this theorem, you have to understand, one, you need to include all forces that do work on an object. So not all forces, period, just the ones that are actually doing work. And then calculate the net of those forces in order to get your energy. There are a few things that make this useful. So basically, they're just saying if you're going to try and get kinetic energy by calculating work, then the forces you use to calculate your net work can only be forces that are doing work on the object. So you have to be able to, using what we understand about our definition of work and how it has to be a force that moves an object in a displacement parallel to it, then we need to use what we know about that to identify only which forces are actually doing work on the object to calculate the net work if we want to find the change in kinetic energy. It's useful because if you know that the net work you've calculated is positive, then that means the object is speeding up because your final energy will be greater than your initial energy. And we know kinetic energy is related to mass times the speed. So assuming that the object is not gaining mass, it must be speeding up if its final energy is higher than its initial energy. And if it's negative, then we know the opposite is true. It's slowing down because its final energy is smaller than its initial energy. And then it also allows us to think about kinetic energy as work an object can do. So the amount of kinetic energy an object has translates directly into how much work that object will be able to do. Which is why if you swing a hammer at the carnival game, the faster you swing that hammer, the more work it can do on the bell.
Gotcha. So kind of like the more energy you transfer to...
Exactly. You are putting energy into the hammer, therefore it has more energy, and therefore it has an ability to do more work. So a lot of times people's working or functional definition of work or of energy is the ability to do work. I was going to say, I think that's the spot I want to stop